add certain materials during additive manufacturing, and you are able to get a complex alloy, or you're also able to get a composite. So I'm going to talk about these ideas, although my research areas include much more things in detail, but in the interest of time, as well as in the interest that people are attending this talk after the lunch, preferably a heavy lunch. I don't want to put people to sleep. So I'll keep it short, but I'll also, I'll also have a lot of time for questions if you find it interesting. So before that, my sincere thanks to Professor Keshavan and the team from IIT Palakkad who have organized this Atal Academy talk, series of lectures. And I will straight away start with introducing metal AM to a very basic level as I understand it, and as how I would expect people to start understanding it as well. So what really happens is that you have, let us say, a particular blisk, okay, and this is essentially, you see these in aerospace applications, and you want to make this via conventional manufacturing. The route is that you start, or the conventional route is that you start casting and forging the material, and then you slowly, you do some secondary processing. You might roll it, or you might break down the material, and then finally machine it to this particular shape. Now, the problem with that is that many materials are not very machinable, and these will be expensive. So the post casting operations are generally very expensive. So there is always a need for an alternative route that can not only maximize the production time, minimize the production time, but also make sure that issues related to machining can be minimized. So if you see, it's generally a 2 or 3 step process. But if you look at additive manufacturing, all you need is a CAD model of the same and to scale. And once you feed it into a 3D printer and you add in the metal powder that you want to print, what you can actually get is the same component. So this essentially reduces the number of steps that are required. You also get a very high buy to fly ratio. So the reason is that the material that you are inputting or you're using is going to be more or less fully used. So that is one of the greatest things about additive manufacturing, is that once you create the component, whatever the leftover powder is, you can recycle it by many other means. Of course, there are some powders which cause issues as well, but more or less the buy to fly ratios are close to 1, which is very, very rare if you look at conventional manufacturing. But despite these advantages, the problem with metal additive manufacturing is that it is still a little expensive, and there are niche applications for this. For example, now the aerospace as well as the space program in India is now looking to adopt it. We have many eminent scientists who are working in this direction, and a lot of progress has already been made. So if you can see, this is essentially a fuel nozzle, okay, and this is used in aerospace applications. Of course, we can have design of much more complex parts with additive manufacturing, and we can make it very easily. The other application, which is of course niche again, is that you have these biomedical applications. So you see, you have some issues of hip fracture, or you say you want to put an implant, and the design of this implant has to be customer specific or rather patient specific. Then in that case, additive manufacturing comes to our rescue, in the sense that we can optimize the shape as well as the dimensions of the part so that we can give it to a patient. Of course, it's, we know that this field or this processing method is a little expensive, but if we have targeted applications, we can save costs and also save time. Now, I'm also going to look at the different types of additive manufacturing methods, and some of them are like this. Let me just hide this. Sorry for this. I don't know how to hide this. I hope it goes away. Okay, I'll just go back. Yeah, it's fine. I think the heading is not clear to me. Anyway, so the point is that if you look at the most popular ones that we have, it is called as the laser powder bed fusion method. Okay, and generally these are powder bed methods. This is the most popular one. You also have got selective electron beam melting. In both cases, generally you have a powder bed where powder is laid over a bed, and then whenever you print a particular 2D slice of the component that you want, let us say in this case a gear, you just have to print that, or the laser runs over the material in that particular pattern for that 2D slice, and then the bed retracts downwards, which means that it is a layer by layer addition of material, and in the end you can obviously imagine that you get the component. The remaining powder can be taken out and can be recycled. The other method, which is also very popular now, is called the DED, okay, directed energy deposition, or it is also called as LMT. Some people use these terms, alternately. And in that, you can clearly see that powders are being fed to nozzles, and a laser is directed to these powders, essentially melting it in situ. So this can actually lead to you can see that if the robotic arm that is containing these nozzles as well as the laser beam is moving in certain directions, you can print according to the way you want the robot to move. Okay, so this is another very nice method. And the advantages are clear. You can see that it works like magic, right? You're creating material, looks like you're creating material out of a torch. A more recent method is the binder jet method, and this is aimed to be a little more cheap, and for, let us say, end users who would want to do things at home, is the binder jet method. Of course, it's not been evolved to such a use yet. But what really happens here is you mix the material powder that you want to print with a polymer that can be cured. Okay, so if you have, let's say, even multiple materials, you add the powder and you got a binder which is then laid over this particular this bed which contains that polymer, and then it is cured. So you cure these things at some by UV light or some kind of a energy that will essentially evaporate, or it will dissipate these polymer particles which are attached, or the binder particles that are attached, and then you have the whole part. Later on, you could also have sintering, because what you have is a structure which is made out of powders, right? And these are all clumped together. And then you can sinter it. And once you sinter it, the energy releases all these excess materials that are sticking to that particular powder metal or material that you are going to print. And the sintering process, of course, has its own advantages and disadvantages. Nevertheless, we are not going to go too deep into that. I'm going to concern myself with two topics that are of a lot of interest. Before that, I'm going to talk about a little bit on the power sources that we use. Of course, we use this laser power source. We can have different kinds of laser power sources, which you might have already heard in the previous few lectures. But generally, a laser power source, you need a certain focusing lens, and that essentially falls on the bed, and you can print wherever the laser is running. You can also have an electron beam sort of a power source, where you have the electron beam being shown on this particular bed. Okay, and clearly the problem with the electron beam melting is you definitely need a vacuum chamber. On the other hand, laser, you can still work in an argon atmosphere or inert atmosphere. But of course, in the electron beam case, you need to present vacuum. So you can clearly see some disadvantages or advantages related to both these methods. Of course, electron beam melting, it is generally heard that the dimensional accuracy can be greater. And it is also used for, let us say, printing, these superalloys more often, of course, for aerospace application. But having an electron gun itself is a costly problem. Instead, a laser bed, is relatively cheaper. Of course, there are some issues with if you go for very high power lasers as well. But generally, you can do some kind of printing in situ in some cases. For example, directed energy deposition is best suited for laser methods where you don't need a vacuum atmosphere. You could create a local environment of inert gas so that printing can be done or remanufacturing can be done. This was one of the themes in Singapore as well, where I went, they were looking at remanufacturing components in situ if there is some damage to it. So I'm going to look at powder bed methods first. And if you look at the powder bed methods, of course, not a lot different from your LMD or your DED method, but powder bed is generally taken as the reference these days. And then later on, directed energy deposition also has got some similarities. But we'll first look at the powder bed variables. Okay, and if you look at that, if you have a powder bed, if you lay down a metal powder on it, you shine laser on it. What you need to understand is that certain issues such as the laser beam diameter, the hatch distance, that is essentially how much is the spacing between two concurrent runs of the laser. Okay, that is called a hatch distance. Hatching is essentially the spacing between one laser run over the other. So you look at it in terms of a hatch overlap. Okay, and that hatch distance is maintained throughout the bed to ensure proper fusion. The third thing is layer thickness. Of course, a lot of research is going on to optimize the layer thickness as well. You can clearly imagine that the power density required will be higher if you have a higher layer thickness, because the laser has to go and input energy into that much depth for the material to fuse. So very simple ideas, Of course, these are all parameters that are optimized either by hit and trial or by conducting some simulation studies of the material. And you can see it's of course a very rough picture. Here the hatch distance, there is no overlap. But what really happens is when you run the laser, let us say in a particular pattern, here we're just doing one single scan and we are doing it side by side, you see that the formation of these very nice sort of a mesoscale structure, and this is called as your, if you look at them individually, they are generally constitute a single line of a laser run. Okay, and they have a semi-elliptical shape, which means that the liquid which is being melted is melting within this particular zone. And of course, you will have other things which is very similar to that you see in welding engineering, that you have a heat affected zone around it as well. All right. So generally, what happens is the semi-elliptical or semi-circular zones are overlapping, and you see a very nice structure which looks like this. Okay. So you can clearly see the arrows here are showing you the direction in which your solidification occurs, or the direction in which the solidification front is generally moving, or you could say the thermal gradient is also around this certain direction, which leads to the formation of columnar microstructures. So you would see a lot of these very nice dendritic and columnar structures in 3D printed materials when you look at the microstructure. But as such, if you just consider the melt pools, these constitute the mesostructure of the material. Okay, this is slightly in the scales that are higher than the grain size of the material, and hence are referred to as mesostructures. Okay, so we have done a lot of work on mesostructures, but I am not going to go so deep into it this time. I'm going to talk about mostly the process variables and how they influence printing. Okay, and when you talk about the process space, the most important one is the energy density. And energy density can be encapsulated or can be found out from this particular process space, which has been popularized by a group in CMU. They started, the picture is from their research as well. So if you see this, you can clearly see that on the x-axis you have velocity, on the y-axis you have power, and this power is nothing but your laser power. So if you clearly imagine that if you are using very high power and low velocity, the laser is going to be on one spot for a longer amount of time. So what I mean to say is that if you look at the left side of the curve and you go a little, if you go vertically, that is, I'm increasing power and I'm keeping low velocity, I am going to have higher penetration of this laser, or rather it's going to be directed more deep into this particular powder bed, and it's going to cause something which has got a very high aspect ratio. So this melt pool, instead of being, or rather you could say it forms semi-ellipse, which has got a very high aspect ratio, right? And this aspect ratio also means that the melt pool is now going to be very, very deep, okay, but not very wide. And this causes something called as keyholing. And keyholing is a problem because it is associated with a porosity as well. Okay, there are many videos to show that. I don't have that unfortunately today, but or at least the clarity is not very good there. But when you're running the laser and you form these keyholes, what really happens is that a cavity is formed, or rather a porosity is formed at the end of the, or you could say the edge of the melt pool with the laser bed. And if you increase the velocity, what you can expect is that the energy input to the bed is not going to be enough. Enough for what? Enough for melting the material. And hence what can happen is in certain regions, the material is not completely melted and you will leave some kind of pores, or you could say lack of fusion pores, because the material could not fuse in the amount of time you spent. So as you increase the velocity, but keep the power low, which means I am at the bottom right of this figure. If you look at the bottom right of this figure, you see that there are several of these lack of fusion pores. And that is also a bad news, because for fatigue and fracture is okay, but fatigue, definitely lack of fusion is an issue, because you see that cracks will nucleate from these particular areas. So bad news again. Now, if you go for very high power and very high velocity, generally instabilities come into the picture. And these instabilities lead to the formation of beads on the top surface. Of course, these beads not only cause dimensional issues, but these leads to ejection of material, because it's just rapid printing. So you have very high power and very high velocity. So this rapid printing actually results in ejection of material, and also some kind of Maragoni convention results in the formation of beads on top of this particular printed material. Okay, so we want to avoid these three, because these three are essentially giving us defected materials. So what we are looking at is a window, and that is highlighted here, with a particular trapezium, and that window is where we are going to print the material. This is a very well known idea in 3D printing, and the idea behind this is developed from the idea that we need to avoid defects. And this is of course done by optimization, or rather you could say it's a brute force method. You just try several runs, and whatever works in that window, you particularly find that region and you try to see which is the best area in the window to operate. This other thing you could do is you can also change the scanning strategy. See, in general conventional manufacturing, you don't have so many options. You generally come with an idea that you have a furnace or you have a, let's say a vacuum arc melter. Generally, you put the material there and then you cast the material in different types of castings, of course. But here, what you can do is you can play around with how you're going to build the material. And in that case, how you're going to melt the material or the sequence in which you can melt the material. And here you can see that the direction of arrows that are there here, that are being shown here, is just showing the direction which the laser will move. So you can have very different kinds of hatching patterns. It's called hatching strategy. So one could be your checkerboard. Okay. Checkerboard, of course, you will have something which is very similar to that of chess, right? You see a checkerboard or a chess board, we will see that each pocket has got a different color. So which means that in each pocket, the directions will be quite different. You could have an island strategy or a stripe pattern. Stripe pattern I'll also talk about in a few minutes. But island strategy is every island will have a different direction of printing. And this actually helps in homogenizing the grain structure. Because you can imagine that because we are printing in a particular direction, there is going to be directional solidification. And to avoid that, you can try to print in different directions so that the material does not become overly heterogeneous or overly anisotropic. If you want to ensure isotropy, you can change the scanning pattern or the hatching strategy. All right. Then, if you look at the laser power and velocity, the main concerns that are associated with it, we just break it down the problem to a laser power and velocity thing, because other parameters we assume are we are going to use standard for the time being. And if you look at it, what really happens is, if you look at a single track melt pool, generally additive manufacturing literature or even people who work on additive manufacturing, they look at a single track. That is initially to make sure that their particular laser speed or whatever power they are using is enough to melt the material in a stable fashion. Okay. And what really happens is they observe this melt pool bead and take the cross section to examine the quality of the bead. Okay. And if you look at it, it's very, very clear here that if you consider these particular the different powers for a particular velocity, you can see higher power leads to a deeper melt pool. Okay, and you can clearly see over some time it will lead to keyholing. Okay, keyholing and its problems, I'm just going to come in the next slide. But the same thing, if you use a fixed power and you reduce the velocity, or you rather increase the velocity, you see that the keyholing disappears and you could have a better aspect ratio, right? So we are always moving towards a zone where you have intermediate velocity and intermediate power, laser power. And that is where you get a reasonably good looking melt pool. You don't have it too deep. You have it at a very reasonable aspect ratio, which is very, very close to 1, let us say. And people love this because they say that the quality of the material, or we could say the quality of the build, is pretty nice. Of course, there are exceptions, and we will come to that. And that then we talk about the idea about the keyhole. Okay, what happens if you have a keyhole is that there is a particular pore that forms at the bottom of this particular keyhole. So we are looking at different defects that come up, and we are going to focus a little more into that because the talk is going to include certain defects or certain problems with printing, because that's why I'm talking about processing as well as material challenges. But processing challenges itself, I'm going to go with first. And if you look at this, there's a keyhole geometry, and you see that at the bottom of the melt pool, there is a pore. Okay, and what we have done is we have used very high power but low velocity. So you can clearly see that the laser is penetrating deep into the material. And if you use balling, or if you use, moderate speed and moderate power, in fact, it should be high speed and high power, not moderate speed and moderate power. So then what happens is that you see that the material balls up. And this balling up the material, you can clearly see, is not going to lead to very good fusions, because the material is supposed to go deeper. You would expect that, I want to print a material that the melt pool is so deep that it can sort of cover a certain amount of bed. But what really happens is the material pops up like a ball and it stays on the surface. Not at all good because it leads to lack of fusion also. Of course, as you can see, lack of fusion is causing these kind of pores. You can clearly see that very, very clear defects are there when you have the several melt pools, but done in a very high speed and low power fashion. So you can clearly see that defects are generated in this sense, very bad for fatigue as well as ductility. So again, process pace is, that is why very, very critical in additive manufacturing, especially powder bed methods, where you are going to look at power and velocity. Of course, if you look at DED and other methods also, power and velocity do come into the picture. Of course, there is going to be a different version of that. The control parameters can also be different. In laser powder bed fusion, you have, of course, bed thickness. In DED and other methods, what you can have is the rate of flow of the material. That could be an additional parameter. Then you have some unavoidable pores, and these are called the metallurgical pores. And metallurgical pores, it doesn't mean that metallurgy is bad. The only thing it means is that these are unavoidable, and that's because gases get trapped in the material, and those gases do not get fully released when you do this printing process. They are highly unavoidable, but they are much, much smaller in dimensions, and you can live with them. Of course, you would want to minimize them, so the quality of the powder becomes very, very important. And you can also see that the keyhole pores, of course, I had shown you in a single bead case, but if you look at the whole build, you see that keyhole pores evolve into such nasty, very irregularly shaped pores, and they're very bad. They really damage the whole material. So you want to avoid. So if I cover my research in additive manufacturing till now, I have these 6 parts which I concurrently work in. I work on in situ alloying, ex situ composite making, as well as understanding the cracking of super alloys. That is a very important field because most of the super alloy powders that we get very nice to work with. But the problem is the moment you start printing them, you form cracks. Okay, that is mainly because of different kinds of issues such as constitution undercooling. And you can also have compositionally graded alloys. That is, I'm going to change the composition from one end to the other. So I can essentially do an Inconel 625 or an Inconel 718 with another alloy, let's say cobalt chromium. I have also done this. Now we are working on doing different compositionally graded alloys because we can tune the properties on one end and we can change the property of the material on the other end. So it's like, essentially joining a material, giving it a compositional gradient. So that is one more area. And then the most important thing that I generally work on, of course, this is the core part of my training, which is fracture and fatigue enhancement of 3D printed materials, and also working on the structure property correlations in 3D. So these are the 2 topics I mostly work on because you are looking at the structural integrity of the parts. But for today's lecture, I'm going to focus more on the processing importance or the processing details of part 1 and part 2, which is mixing of materials. That's a very, very big challenge because you're going to make cheap materials, you're going to make cheap products, and if you're going to mix them, how are you going to ensure quality? So that's going to be the first question. And there can be 2 methods to do that. You can consider in one case that the materials are getting into an alloy, and the other case where you consider that you're only trying to make a composite. Okay. So let me go to the part 1 first immediately without delay. We are looking at in situ alloying. Very nice work because we were talking about tackling a very important challenge in additive manufacturing, and we felt that we did a reasonably good job in resolving this issue. Okay, and the issue is read like this: there is a problem of porosity and inclusion. Okay, and this is a dilemma because there is a trade-off between porosity and inclusion, and I'm going to explain what this really is. So if you look at titanium niobium alloys as such, okay, why I'm talking about titanium niobium is going to now, I'm going to talk about that because we are doing in situ alloying. We're trying to make a titanium niobium alloy, and I say that we are making it for biological implants, okay, or orthopedic implants. So the idea behind using this will come to the picture now. If you look at an orthopedic implant, it supports, let us say, your bone, right? And your bone is a structural material. So bona fide structural material, nature's best structural material. But unfortunately, we find ways and means to get a fracture. Okay. Of course, human beings find ways to do all kinds of destructive things, but they can do some self-harm or, without or with their knowledge sometimes. And such a fracture, when it occurs, you generally want to, or doctors want to put an implant, okay, whether you like it or not. And an implant, generally, you would expect that, if you have the stiffness of bone, which is given as 3 to 25 GPa, one would expect that the implant stiffness should be similar, right? Because you're going to go with something which has got the same stiffness. But there is another school of thought that would say that I want a stiffer implant, right? There could be a school of thought which says I want a stiffer implant because let us say there is a problem that I put excess pressure. I don't want my fracture to become exasperated, right? I don't want it to become worse. So the problem with that approach, or the problem with that thought of having a stiffer material as an implant, is that if you look at the bone and if you look at how it calcifies, if you look at the normal condition of it, this is how your calcium phosphate mineral looks like. Okay, it's got this very porous structure, and after fracture, what really happens is your body, or after fracture, of course, your that part of the bone is broken. But if you look at the mechanics of the human body, if you look at the supporting structure, the most important force or the most important stress that is applied on bone is the compressive stress. Okay, there's a little bit of bending, but you never apply tensile forces. Very rarely you do. If you apply tensile forces, you are in trouble. But if you look at a person standing, you can clearly imagine that the bone is in compression, right? And if you look at, if I put in an implant that has a higher stiffness than bone at the fractured area, and I say that I'm now going to rest on this particular material, I can, because when you start walking after a fracture, you tend to put little and little weight on your leg, right? That's how you recover from an injury. People who have seen this happen to themselves or to their relatives, they have seen that people at the end stages, when they start learning to re-walk, they essentially apply little pressure and do that. But if you use an implant which has got very high stiffness, the problem is that the implant will take all the load. And this sends a bad signal to your brain that I don't need to calcify the bone enough because my I don't have to put as much weight because this implant that I have inserted is taking care of the load, right? So this problem actually results in something called as osteopenia. Osteopenia is nothing but that the body does not calcify the bone enough, thinking that there is already an implant which is taking the support. So I don't need to calcify the bone enough to take that general load that you need to do for running or walking or doing heavyweight exercise. So in that case, what happens is your bone doesn't recalcify to the same extent. And this leads to further injury. Let us say you remove the implant, which is much more stiffer, and then you start reusing your body the same way you used to. Osteopenia will result in the fracture of the bone again. So what we result, or what we come up with, or what doctors came up with the idea that let's not make an implant that is stiffer, but rather an implant with the similar stiffness of bone will help, because it won't really take up as much stress as a stiffer implant would, which means that the bone will also get sufficient or load, or the load sharing will be more better with the bone, so that it can also grow or recalcify to the same extent as it was when your bone was not broken. Okay. So if you look at the stiffness of biocompatible materials, now this is where the question comes in and why we are using titanium niobium alloy. If you look at stiffness of biocompatible metals, generally if you look at titanium alloys or steels or different grades that have come up, they are generally 100 to 300 GPa. Okay, these are about 4 to 5 times higher than what your bones stiffness is. And that's not good news, because you're always going to make stiffer implants which are going to take most of the stress. Okay, so stress shielding is a problem. But if you look at titanium alloys with the addition of niobium and tantalum in solid solution, that is, if you alloy them, what you really see is that the elastic modulus drops. Okay, if you look on the x-axis and you look at the tantalum content, or you could even say niobium, both of them have similar effects. You see that if you keep increasing that, you see that the elastic modulus drops very, very low. Okay, it can go up to 84, but you can go even lower. That's what we want to essentially ensure, that you have a lower. So there is definitely an advantage in alloying a certain amount of tantalum or niobium with titanium. Okay. Similarly, what you also see is that now if I add a certain amount of niobium and I age the material, aging is nothing but heating the material for some time, I can see that your modulus changes, but the modulus changes only for alloys which have got 36% niobium. Okay, but if you have 44% niobium, you don't have much change in modulus, but you can strengthen the material. See, strength is very different from stiffness. Strengthening is important to prevent failure, but stiffness is important to reduce your stress shielding. So if you see 44% niobium, we are very happy with it because you can strengthen the material without changing the stiffness too. So that is where again the alloying part comes in. Generally, we take about 44% niobium for alloying with your titanium. Now, when we come to concept of mixing of powders, this is another challenge. It's not as straightforward as one would think. You can't just put one powder after the other. You need to mix them, and you need to mix them. There are various prototypes of mixers. They are custom made. Some are tumbler mixers, and some are centrifuges, which are designed in a way which rotated at a defined RPM to ensure good mixing. Again, a field of interest in additive manufacturing on how to do better mixing and how to ensure that it's more homogeneous. Of course, no method is perfect. We always get some kind of heterogeneity. But since we are going to go for alloying, it really does not make that much of a difference. And if we see that, what really happens is that we are going to now put a bed. When you're laying down the bed, you're going to ensure that at least each portion of the bed, if you're considering a micro volume of a particular bed, the composition should be close to titanium 44% niobium, very, very close to that, and that should be okay. All right. And in directed energy deposition, the thing is you are going to use the two nozzles and you are going to adjust the velocities of these in such a way that only about you could say 56% of titanium comes in at a particular point of time and 44% of niobium comes in or tantalum comes in at a particular point of time, so that every shot of your whenever the material is released from the nozzle and comes down to the laser is essentially melting titanium 44% niobium. That's the entire idea of that. Now, let's say you have mixed these, and generally this is a schematic and very, 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 very close to the actual situation. Your titanium powders are generally made by gas atomization. There are different types of gas atomators that are there. You generally get a powder, you're very happy, but the process is slightly more complicated. You have to use a gas atomizer, you have to make sure there's less oxidation. And titanium powders are generally easier to make by atomization. However, niobium is much more harder. Generally, they make niobium powders by crushing. Very difficult to atomize. Niobium has a very high melting point. And hence, you generally crush the material and they have a very irregular shape, unlike titanium. So, this presents another problem. If you look at additive manufacturing literature, mixing spherical particles with irregular shaped particles is also a credible issue, and people are dealing with it. So if you look at this powder mixture, now what you do is you put it on the powder bed and you can clearly imagine the problem now. So as I told you before, niobium has a very high melting point, right? Very, very close or above 1000 degrees Celsius. Titanium does not have a high melting point. So what really happens is your choice of the laser power that you are going to use now becomes critical. Because if you use too high a power, you could evaporate the niobium powder, right? And evaporate the titanium powder because the temperature is too hot for titanium because you're trying to melt niobium, but titanium is also along with it. So you might not only over melt, but rather you will evaporate or it will start escaping. Okay, so that's a problem. If you use too low a power, or the power velocity combination is such that the energy density is lower, it means that your niobium will not melt. It will remain as a particle, and that's a problem. Okay. So what really happens in the microstructure when you look at it is that certain regions will be alloyed very nicely with grain structures, but you will see some pieces of niobium. Okay. So and also if you don't ensure complete melting, you will also have keyhole porosities. Okay. So different kinds of defects can form, and I'll show you how they form. Okay. Porosity and inclusion both are there when you do some kind of an in situ method. And the idea of keyhole porosity, I'm now coming to the actual point of it. What really happens is when you have a laser moving in a certain direction, this is how it exactly forms. And you see that there is a melt pool that is very deep. What really happens is that the melt that has formed on one side, because of the injection pressure, or you could say that the pressure created by this melting is going to now make the melt pool or the side of the melt come back like a wave. Okay, so this is the back pressure that is applied. So there is a back pressure when you're doing this melting. You're going forward, and there is a melt pool back pressure. So this melt pool back pressure pulls back, and then due to the meniscus action, the melt pool wave comes back and fuses with the one on the adjacent wall. So you can clearly see When it fuses with the adjacent wall, you can clearly see a porosity forming at the bottom. So this is the problem that actually happens in the formation, or rather, this is what actually causes your keyhole porosity. So there are many theories. Of course, this is one of the models that are there. Of course, nobody has completely found out what it is. They're still looking at these ideas in a more clear fashion, but more or less there is some kind of consensus that this is the kind of instability that leads to the formation of a keyhole porosity. Okay? And now we are going to examine the parameters which can cause different types of defects. Okay, so if you use very high power, what it will do is it will melt the niobium surely, but you will, of course, if you have low speed, you see that the keyhole is going to be very long, or you're going to have a melt pool that has got a very deep or it has got higher depth than your width, or a very high aspect ratio. So that will cause keyhole porosity. Of course, you will have less inclusions, but very high porosities when you use high power and low speed. And if you use generally these moderate power and speed combinations, what really happens is that if you use these combinations, you get a very unstable melt pool. That's what we observe. The melt pool is very unstable, and you have a lot of these unmelted niobium particles, which are looking like this very bright colored round things. Okay, these are unmelted particles. The melt pool looks really bad. Okay, your single bead test looks really bad. And if you use this low power, low speed combination, okay, what you really see is you're going to have unmelted niobium, but you see a very nice melt pool with a very good aspect ratio, very close to 1, and you say that this is pretty nice. I'm going to go with this. And generally, if you do that, the problem is that you find terribly lot number of inclusions. There are two problems with that. One is inclusions are going to cause fatigue. Second thing is that you're not going to get the actual alloy composition that you were targeting. You wanted an alloy composition of titanium 44% niobium, but you might go to titanium 40 niobium. That's directly going to raise your elastic modulus of the alloy, right? So you don't want that. So low speed, low power has the problem of higher inclusion. Whereas if you use higher power, melting is more. Niobium definitely melts, but you will form a keyhole definitely, and that will lead to porosity. So what really happens is that we now have a clear trade-off. One is you have a very high power and low speed combination. One is low power, low speed combination. Or even if you look at low power, high speed combination. I'm sorry, here I should have written high speed possibly. Even if you use that, you will always have either these porosities or inclusions. So that's always a problem. So this dilemma has to be solved. How do we optimize this? Various methods were tried. Some people tried remelting strategies. That is, once you do the bed, once you do the printing, you again run the laser at the same pattern so that the materials are remelted and homogenized. But that did not solve the problem. Okay. So what we tried to do is we reassess the strategy. We thought that, okay, let's just look at what we are doing. Let us see, we are just doing a single, let's say we are looking at a single track scan, and we are assessing the properties. Okay, so that's a viable strategy because most of the additive manufacturing people or the researchers are doing that. We said that we are now going to change the hatching strategy a little bit. We are going to do single stripe. It's very different in from a single track because of course your laser is going to run, or you could say that the net motion or the total average motion of the laser is going to be along a track, but you are going to zigzag it. So you're going to move it in a particular sinusoidal wave, just like a you could see a longitudinal wave, or you could see a electromagnetic wave, right? So it looks like a zigzag pattern. So you're going to run that along a certain axis, okay? And this is called as a single stripe strategy. The other thing we changed was that we used laser with a different profile. Now you see, if you have a Gaussian profile, typically what really happens is that the energy is concentrated in the middle, and then you have energy reducing at the side. So this is typically the laser profile that people use for printing. Okay, for whatever reason, it's a default in your additive manufacturing machine. And if we use this particular Gaussian profile and a single track method, we have several pores and unmelted niobium. You clearly see we have done a tomography here. This is a tomographic image plus a microstructure, and you can clearly identify pores as well as unmelted niobium. So this is a problem. Now, if we change it to a top hat strategy, what it does is that your laser beam, if you look at it, the whole cross section will have enough heat. Okay, and this heat will be essentially focusing uniformly over this particular beam. Okay, and when I use this, And when I go for higher power, so see, if you had seen the previous picture, it was about 350 watt, 350 watt, 350 mm per second. But if you go for higher powers and you use top height profile and single stripe, you immediately see that the pores and the unmelted niobium has drastically reduced. So if you look at the tomography images, you can clearly see that these spot patterns, okay, especially the pores which are green in color, they have completely disappeared when you use 650 watt and 950 watt, which is high power, right? We're using high power, high speed. Here the velocities are also 650 mm per second and 950 mm per second. So they're very, very high. And you still see that you have a very, very low amount of pores. Of course, the keyhole porosity is completely eliminated in these. However, you have some inclusions. Of course, in the 950 case, the inclusion level is also much, much lower. So if you see, we are using a very high power and velocity combination, but still there is no keyhole porosity. We completely removed them. Not a single keyhole porosity was identified. Okay, at least via our tomography measurement, which has got a reasonable resolution. Okay, whatever there were metallurgical pores that cannot be avoided. So how does this work, right? I mean, you might want to ask that, you're using high power, high velocity combinations. It should not work because you see that clearly you will have all kinds of instabilities that come in during processing. So we did a very simple simulation. This is a very non-standard simulation. This is using, COMSOL. I think this is a heat simulation that we did. What was essentially done is heat mapping was done. So whatever heat transfer is going to come, the radiative heat transfer, as well as convection, that those parameters and conduction were also considered to model how the melt pool will behave for a certain power velocity combination. Okay, and this particular signature that you see moving is essentially the heat signature. But you could also assume that the heat signature is going to be complementary, or rather it's going to be the same as that of your melt pool, right? So your melt pool is also going to appear like this, because wherever you're heating, you're assuming that your melt pool is going to form, or the material is going to melt in this particular region. And you can clearly see, if you're going to do a stripe scanning strategy at 350 watt, 350 mm per second, what you really see is that when you move in a zigzag fashion, the direction of the melt pool motion is parallel with the direction of the motion of the laser beam, right? That's very, very clear. And you see that the pool motion and the laser direction motion is the same, and there are going to be ripples that form behind it. But if you look at the keyhole, the melt pool aspect ratio, we're going to take a cross section at one snapshot. See that very nice aspect ratio, very close to 1. Of course, here it's very close to 2, I know. But if you look at half the width and this depth, it's very close to 1, right? So you're very happy with it. And of course, even if you look at the other cross section, when it is spreading around, right, wherever, if you consider even the ripple formation, you see that even that is not too wide. It's okay. It's not too wide. Nevertheless, the heat distribution is very, very concentrated. Okay, and remember, this is a Gaussian profile laser. If I use high velocity and high power, 950 watt, 950 mm, and I'm still using the stripe scanning strategy, but I'm using, let us say, a top hat laser profile, what I see is that I'm having a humongously large pool. Okay, and if you observe that, the laser direction and the melt pool motion is now perpendicular to each other. Now that's very nice, in the sense that what really happens is that you're allowing the melt pool more time to melt. Okay, the other thing is your aspect ratio is now going to be much, much lesser. Okay, that's very good, because in the sense that you don't have a very deep melt pool, you have a wider melt pool, which allows more material to melt, right? And you're not going to form this instability of keyhole, because your waves are not going to travel from one wall to the other, just as in the case of a deep melt pool. In the case of a shallow and wide melt pool, the advantage is that you are going to melt more material. You also see that the motion of the melt pool is much, much slower, which means that you are giving more time for solidification to occur, more time for alloying to occur, which means that the material is going to be much more homogeneous, or the alloy is going to be much more homogeneous. So the width that is artificially increased by this stripe scanning strategy, as well as the top hat laser, actually gives us the advantage that the alloying becomes better. You completely avoid keyholing, and hence the inclusion as well as porosities come down. You don't have the trade-off that there are going to be more porosities or more keyhole, more inclusions. if you use a particular strategy because of this particular change that we are using higher velocity as well as higher power, but using the stripe scanning strategy and a top hat laser. So this kind of a experiment actually tells you that just relying. So if you had seen the earlier slides, I had just shown you a picture that moderate speed, moderate velocity, you will have a very bad single bead, right? A single bead is not very well fused. But if you run this for a whole build, you see that you are now getting a very good microstructure, which I will show you. But if you look at it, the melt pool is very nice. You get very negligible porosities. Of course, zero porosities in terms of keyhole ones, but also very good melting, which means inclusions are very less. Okay, so your aspect ratio control can be achieved, and you may not necessarily rely on a single bead test. So this is a very different thing. We generally rely on a single bead test to say that if my melt pool in a single bead looks good, I go ahead with it. But no, sometimes you will have to actually print an entire stripe or an entire bed to figure out or to make sure that your melt pool engineering is complete. And if you look at the resultant microstructure, we saw very nice microstructures. The top one, if you look at it, is 350 watt, 350 mm per second. And you see several number of grains here. Okay. The microstructure has got, or rather, this is an EBSD image, and you can clearly see that the preferred orientation that we want is your 001. Okay. And these are the red grains. But if you see, there are all kinds of grains here. Okay. It's complete distribution of all kinds of grains. This is not really good news, especially for implants. You need directionally solidified ones because you need that your Young's modulus is lowest along a certain direction. That is generally what you expect. And for that, 001 is the softest, or you could say the less stiffest direction. So you would want the 001 texture, 001 texture to be dominant. Unfortunately, with 350 watt and 350 mm per second, you don't get a good texture as well. And we'll clearly see why the reason, what is the reason for that. But when you go for 650 watt or 950 watt ones, you see very few of these stray grains, which have got a different orientation, say 111 or let's say 101 orientation. Very few grains are there. It's predominantly columnar with a single orientation of 001. Okay. And when we zoomed in into those locations where your stray grains or blue colored or green colored grains were, we saw that there was a niobium particle sitting there. And this niobium particle essentially leads to directional solidification in a certain direction because it acts as an inoculant. Okay. So the problem of inclusion is now compounding the issue of microstructure as well. If you have an inclusion, it will essentially lead to bad microstructure also, the ones which you don't want to have. So that's why reducing the inclusion level is actually beneficial in getting better microstructure. So this is the third reason why you want to have lesser inclusions. Now, if you look at the mechanical properties, so we want to check how does your mechanical properties or how does this material perform, and we want to specifically look at the UTS as well as your ductility. We need more ductility generally, especially in compression, but this is a tension test just to see how it works. In tension, if you see the 350 watt, the build with the 350 watt, 350 mm per second, this laser strategy, we see that it has a higher Young's modulus, slightly higher, 66.5, and a very low ductility. Whereas when you use the 950 watt one, you see that its stiffness is much lower. It's about 57.5, very close to what we want to achieve. So we want to go lower as possible, but 57.5 is very good. We can live with it, and you see that your strain to failure is pretty good. So your material, if it is overstressed, will not undergo catastrophic failure. So you can be reasonably safe about it. So that's one of the things, we clearly saw that one of the things or one of the advantages is that we have a win-win situation here. Not only are we reducing the inclusions in the material and porosity in the material, but we are also making sure that we get the right microstructure. That's a big win because we never thought that this effect is going to come in when we reduce inclusions. Okay, we were initially thinking there is some kind of a columnar to equiaxed transition, and that was not happening because basically your niobium particles acting as inoculants and growing stray grains in different directions. So engineering the material or resolving one porosity to inclusion dilemma is also giving us an additional gift of having a very good microstructure. Okay. Now I'll move on to part 2, and for the next 40 minutes, I hope you will like this part because it uses a very nice material, one which I love to work with, and it is very well known as the bulk metallic glass. Okay, and bulk metallic glass, of course, you might get an idea that these are something like silicate glasses. It is definitely not. It's a metallic glass. So it is a metallic alloy which has got several components, and I'm going to make a composite with niobium. Okay, so this is a very recent study. This paper is under the second stage of review. We hope to have it accepted very soon, but I wanted to show something new, and hence the inclusion of this. Of course, it's a very interesting topic as well, one of my favorite topics, because it's a very strange advanced material. Okay, so let me jump directly into it. Bulk metallic glasses can also be used for implants. And the reason for that I'll come to in a few slides. But you can clearly see here a very shiny piece of implant made from bulk metallic glass. Okay, and surgical instruments as well. It's very shiny, and it's very likely to have that shine for many years to come. So that's a very big advantage. Okay, and the reason for that is bulk metallic glass has got very good wear resistance, very good corrosion resistance, and thirdly, it has got very high biocompatibility. So a lot of research groups in Germany and China are considering these metallic glasses, zirconium based ones, as a biological implant. Okay, but first, what are metallic glasses? Okay, we need to understand it from a solidification point of view, from a physics point of view, what it is. So if you have a liquid, okay, liquid metal, of course you're going to have a liquid metal high temperature, and you start cooling it down slowly under equilibrium conditions or semi-equilibrium conditions. What you generally do in a casting is that you cool it down, and then when you cool it down, suddenly there is a change in the volume. Okay, there's a very big shrinkage that occurs, reduction in volume, and there is a discontinuity in this curve, right? You clearly see discontinuity, and that is where you say that your crystallization has started or a nucleation event has started occurring. And this nucleation event will essentially lead to the formation of a crystal. And as you go down, the crystal structure anyway does not change much. Of course, you can have some kind of rearrangements or growth of a crystal, but you will see that the volume shrinks and it becomes a certain volume at a certain temperature. If you go to room temperature, there is a certain limit or the certain density that the material achieves. Now, you will also see that of course you will have a polycrystalline material. In most cases, yes, single crystals can be grown with some strategies, but in most materials you will have the formation of polycrystalline materials, polycrystalline metals. Okay, and if you look at it, it is you have this different grains. There's grain 1, grain 2, and grain 3. There are 3 different grains that exist, and you clearly see that there is a boundary separating them. This is how a crystal grows. Okay, however, I consider a situation where I take the liquid and I rapidly quench. And I rapidly quench to the extent that I am retaining the structure of the liquid to the room temperature. That is also possible. And that is what great scientists like Paul Dewis actually found out. Bill Johnson also worked a lot on this. Found that the amorphous structure of the liquid, atomic structure of the liquid in a metal can be maintained if you cool rapidly enough. Okay. And he also found that the cooling rate as faster you go will preserve the randomness more, and you actually bypass the nucleation event. So you're able to solidify a structure which is very amorphous, or rather retains the memory of the liquid structure even at room temperature. It's a lot of like metastable materials, but a lot of engineering design has made sure that the cooling rates need not be very, very high. Okay, you can even go for 10 Kelvin per second. Earlier, you used to go to 10 to power 15 Kelvin per second, which is very difficult to achieve, and generally used to have some kind of flash quenching. Or you could even say there is something called as melt spinning, where you have a roll going at a very high speed, rotating at a very high speed, and you splash a piece of metal on it and it rapidly quenches. So you used to have the formation of metallic glass ribbons. But nowadays, the compositions have been changed so much, they add several elements. It causes this principle of confusion wherein your atoms don't know which neighbor to sit with, and you can still retain amorphous structure at room temperature just by quenching at 10 Kelvin per second. So these are the examples of such a material. You see the structure here. What I have done is we have added 4 or 5 elements in some cases. Of course, copper zirconium 50-50 is an exception here. But here, copper zirconium 50-50, you'll have to quench at a higher rate. Okay, you don't really find very thick copper zirconium bulk metallic glasses. And if you look at the others, if you see platinum, palladium, copper, phosphorus, you see there are certain elements that are added in certain proportions. And I can tell you that I won't go into the details, but I can tell you that the proportions are fixed by identifying where you will have a eutectic. Okay, generally, because if you have a larger freezing range, see, if you see eutectic, if you even look at the lead tin system, eutectic point is a point which has got the lowest melting. Okay, or you could say it is closest to room temperature rather, or you could say it is very low melting point. Okay, eutectic metals generally melt at a very low melting point. So what you really do if you keep your metallic glasses composition very close to the eutectic point, or the composition very close to the eutectic composition, what happens is you have a large melting range, and that large melting range means that you can hold the liquid structure for a higher degree or a higher range of temperature. That is what you get. That's very nice, because the amorphous nature of the material remains there for a longer period, and then you just need to quench it for a shorter span of or shorter range of temperature, which is much more easier. If you have to quench from 1000 degrees to 10 degrees in 2 seconds, it is much harder than quenching from 200 degrees to 10 degrees in the same amount of time, right? It's much more easier to do so. So that's the reason why you can have such kind of complex systems. Okay. And the other thing that you observe in metallic glasses is that it got a very confused structure. And the confused structure comes in because you have small atoms, large atoms, different sized atoms, and all these don't want to sit with each other, right? And you can clearly see there is no long range order. If you look at a particular polycrystalline material, within the grain, there is a certain arrangement of atoms. Of course, you call them as BCC, FCC, HCP, several other crystal structures also form. They have some elements of symmetry. In a metallic glass, there is no element of symmetry. They found that there is some kind of short range to medium range order, but beyond that, you can clearly not see anything. In fact, your XRD shows you a very broad hump without any peaks. Okay, and the problem with that, or you could, I would not say problem. The only difference is that in crystalline materials, deformation is modeled via dislocations, and dislocations are essentially moving in a crystal which has got a very well defined crystallography. Okay, so you can define a dislocation, you can understand how deformation takes place, but metallic glasses cannot have dislocations in such a very simple sense. Of course, a lot of people have worked on some of these ideas, but they only came up with approximate models. Disclinations is one model, but of course, very difficult for mainframe, or you could say mainstream metallurgists. Okay. But what is so great about metallic glass? Why are we looking at it? As I said, it has got excellent wear and corrosion resistance, but there are other things as well. So this is how your metallic glass looks like. So you see, you have a steel ruler that you see a lot of people use, of course, in school as well as for measurement. And you put in metallic glasses on the side, they look similar, right? They also are shiny, lustrous, opaque materials, unlike a window glass. They look like this, and you can cast them to different sizes. Of course, there is also a problem. You can't cast it to very large size because cooling rate becomes a problem, which I'll come to. Now I come to the advantage. You just look at this. I'm dropping a steel ball on a steel base. Okay, this is on a steel base. After 2 bounces, the ball stops. You can just take a look at this video again. But if I drop this on the steel base, after a few bounces, this ball stops. Okay. But if I drop the ball on metallic glass, this ball keeps bouncing. Okay. You see that it keeps bouncing for a long time, right? Instead, the steel ball just bounces once. So what you see typically is that metallic glasses have a very high resilience, right? They have a very large elastic region, and that's what I'm going to talk about. Generally, if you see a steel material, you have a yield stress of 400 to 500 MPa and a yield strain of 0.2%. If you look at metallic glasses, the yield stress can be as high as 2000 to 2500 MPa. It can be very high. Okay, so this is about 5 times or sometimes even on order of magnitude higher yield strength. Of course, remember, the Young's modulus is not very high. Most metallic glasses can have Young's modulus close to 60 to 80 MPa. 60 to 80 GPa. It can also go to about 100 GPa. Some metallic glasses do. But most of the ones we are looking at, zirconium based ones, it's about 62. And so that fits under the stress shielding criteria that we were looking at for biological implants. But apart from that, its yield strain is 2%. You see, again, an order of magnitude higher strain you get, which means that it will remain elastic for a longer range of stresses and strains. Okay, that's very good. Number one, because you have very high specific strength, its density is not very high. So you have very high specific strength, but also strength is excellent. These are the strongest materials possible, of course, not looking at diamond, strongest metals you could say, or alloys you could say, and they have also got the highest elastic limit. So very great materials. And this reason for this high elasticity also why your wear resistance is very, very high. Corrosion resistance also automatically comes in because of the complex nature of the material. You have so many alloying additions, it doesn't bind easily with oxygen. Of course, it does corrode a little bit, but the rates of corrosion are very, very, very slow. Okay. Now, some issues with metallic glass is that since you don't have dislocation, there is some other deformation mechanism that takes place. And you have the formation of shear band when you do a compression test. Okay. You clearly see these and you see that, a compression test, you will see some plasticity, but the material does not strain harden as much. Okay. The formation of shear bands essentially means that plasticity is localized within shear band. However, if you conduct a tension test, the problem is that the metallic glasses fail in a brittle fashion. So these materials cannot be loaded in uniaxial tension. That is the only problem. Of course, you can have bending geometry. Bending, it shows reasonable amount of ductility. If you have a good ductile glass, of course, I'll define what is a good ductile glass. It can show very nice ductility in bending, but the ductility in uniaxial tension is very, very poor. Okay. And the reason for that is that the deformation mechanism in metallic glass is very, very different. And if you look at the amorphous subatomic structure, you can only look at things in a cluster sense. Okay. So people came up with two theories. One was the shear transformation zone theory. One was the free volume theory. Both of them are now, placed together because free volume is also important and shear transformation is also important. And what really happens here, the deformation is very simple. You have a cluster of atoms, and to cause deformation, the top part of the cluster will have to move over the bottom part of the cluster. And for that, you need some expansion, because whenever you are in a crowded, atomic structure case, and you want to move a cluster, in a particular direction, you want to shear this cluster, you need to create additional space. So whenever you see deformation mechanisms in metallic glasses, it involves dilatation, or it involves expansion of the volume. And you see that this kind of a deformation takes place, and it has to be associated with extra volume, which is why free volume is an added picture. Okay. So if you have a very crowded space, it's much more difficult for this cluster to move. So if you have more free volume, the cluster is easier to, or easier to undergo shear transformation. And this shear transformation, it can occur in a line where the shear stress is maximum, and you can have the formation of a shear band. So typically, that is how this kind of a deformation takes place in metallic glass. So you form the formation of shear band, and this is how they look like. Okay. So you see that plasticity has localized within the shear bands, and the shear bands act as surface steps or surface offsets. Okay. And plasticity localized on the sides of a shear band, the material is completely elastic. So it is a complete strain localization that occurs in this material. And you can imagine that the strain localization, these bands can cut through the material when you are doing uniaxial tension and break the material. But in compression, the shear bands don't open up, right? A crack cannot nucleate within a shear band, and hence the material deforms more plastically in compression. So that is where the difference comes. Okay. Now we talk about something very, very important related to additive manufacturing of these classes. I'm going to draw a direct correlation later on, but it is important to understand what will happen when we use different cooling rates, or what will happen if we expose metallic glasses to higher temperature. So I'm going to look at first the effect of cooling rate. So when you cool from, let us say, the liquid state, I told you that there could be a different structure when you fast cool it, and when you slow cool it, there could be a different structure. And the reason is very simple. When you do slow cooling, what really happens is your atoms are going to come together and try to form a nuclei. Okay, so it's going to try and reduce the volume. So it is trying to go towards the ideal state, which is your crystallization state, right? So slow cooling allows diffusion to occur, allows atoms to come together, and it reduces the free pockets of volume that were present in the material. But if you go for fast cooling, you're able to maintain the amorphous structure of the liquid for a longer time, or rather at the room temperature, because you're not allowed diffusion to occur, right? So diffusion has not occurred. So the structure of the liquid is frozen with a lot of pockets of free volume. So that is the advantage of cooling it faster. So you can imagine A slower cooled material will have, or the shear transformation zones in that material will find it very difficult to operate because the material is more crowded or it has shrunk more, the free volume is lesser. So a shear transformation finds it very difficult to occur. Okay. Whereas in a less relaxed structure where you did fast cooling, your shear transformation can occur in a much better way because there is more free space. Okay. The other thing is the same effect when you have a metallic glass which was fast cooled, let us say, okay, and then you reheat it. Okay, what you do is you reheat the glass. What really happens is that again this relaxation happens. Why? Because you are allowing thermal input and you are allowing diffusion to occur. This thermal input forces atoms to move and it will start again moving towards the ideal glassy state or the ideal crystallization state, sometimes even crystallization. So you will see that your free volume is getting eliminated. So in this figure, what I'm showing you is a group of DSC images. So DSC images as well as very nice TEM images that these guys have found out. They have done very high resolution TEM and tried to identify free spaces, and free spaces are denoted by black spots. Okay. So if you see what they have done is they have heated the glass for different times. Okay, that's what is being shown as legends in the left hand side plot. And you see they have drawn this DSC curve, and these wells, or you could see this curve that are there, it shows you the amount of unrelaxed glass. Okay, or you could say that there is this much amount of free volume, this much amount of space below the baseline, which is the blue curve, shows you that this much amount of free volume exists. Okay, this has a direct correlation with the amount of free volume. This much amount of free volume exists. So if you see, when you keep increasing the relaxation time, the depth of the well keeps reducing, or the size of this well keeps decreasing, which means that the material is becoming more and more relaxed, or you could say the free volume has reduced. So the same picture is on the right hand side. You can see that the black spots have reduced from a hyperquenched material, which is very fast cooling, to a material which is highly relaxed. Okay. So if you see a very highly relaxed material, the amount of free spaces is very, very less. And you can imagine that a highly relaxed material, your shear transformations will not occur easily. And shear transformations are important because they are the unit carrier of plasticity in metallic glass. So you need shear transformations to get activated. But that cannot happen in a highly relaxed material. The other problem is that if you heat it for too long a time, you start forming nanocrystalline phases. Okay, so within the metallic glass, you will start forming, as you see, temperature is either you increase the temperature or you increase the annealing time. See that you form a lot of these nanocrystalline phases. These are again not good news. Okay, so these are ideal. You could say they're intermetallics and extremely brittle material. So if you test either a very highly relaxed material or a material which has got these nanocrystalline or nanocrystallites that are there, you will see that the material will shatter like your window glass. It is very bad. It's very, very, very brittle. So you don't want this material. So you see cooling rate, if it is very slow or you have a glass which is very relaxed, it sounds very nice that it's relaxed, but it will be very brittle. So for mechanical properties, it is useless. Okay, so that is one lesson that you learn from this, and this is what we are going to use with relevance to additive manufacturing. Okay, and I'm going to come to directed energy deposition now directly, and without going too much into the parameters, I'm only going to consider the laser power. Okay, and of course the speed with the laser scan, but I'm going to now stick with laser power because I have fixed the speed. I'm not changing the speed at all. So laser power is the main parameter that I'm concerned about, which will decide the energy density. Okay. And what I did was this, or what we did was we did this test, okay, and we did a single bead, and we examined the nature of the single bead, and we see that the single bead has got the molten or the melt pool actually contains. You see this amorphous, this most of the semi-ellipse is amorphous, but there is also a very small strip which contains crystalline or crystallites which are present. Okay, and this is definitely what we saw was at the heat affected zone, not necessarily in the melt itself. Okay, and how this was found out is that we did an XRD. We were confirmed by XRD as well as from TEM that these are nanocrystalline phases which are present in this belt of your heat affected zone. All right. Now, what we also try to do is we try to look at what happens at what is the heating and the cooling profile. Okay, this is very, very important because we need to compare it with the crystallization time transformation diagram. So that's very, very important. We talk about this TTT diagram seen in metallic glasses also this is there. But in metallic glass, in steels, it is different. You see the formation of bainite or pearlite or martensite. But in metallic glasses, you look at the crystallization TTT diagram. So there will be a C curve, and if you hit that C curve, crystallization starts occurring. Okay. But if you look at the cooling rates, so this is how we drew a cooling profile using finite element. On the right side is the finite element model there. We did a heat FEM. And if you look at that, if you look at from top to bottom, the heating and cooling profiles are given by a bunch of these curves. So at each point, we can look at the heating and cooling curves. And what we saw was very nice. We are avoiding any form of crystallization. If you see the C-type curve, the crystallization curve, we are completely avoiding it during additive manufacturing for the chosen range of power as well as velocity. It was very good to see that. But then we were like, why is this heat affected zone forming with crystallization, right? Because there is something which might be causing this. What really happens is once you do this scan, and this scan, you're only doing it, let's say, for one bead, you'll not see this problem. If you do multiple scans, the problem is this bed reheats. Okay, you're going to do, let's say, over a bed, continuously, there's going to be reheating which occurs. And if you now look at the reheating, and if you actually compare it with the crystallization curve while heating, which is from the solid state, after it has formed into a solid, that TTT curve is very different. It actually goes and hits the cooling curves or the heating curves of this particular material. We are only going to talk about heating curves here because during heating, this actually goes and hits the TTT diagram for the crystallization during heating, but not during cooling. Okay, for cooling, if you look at it, we had seen that crystallization during cooling it completely avoids, but crystallization can occur when you have bed reheating. So you can say that it is completely unavoidable. And that's what we see. We see that your heat affected zones, some of them intersect this, whereas some of the molten pool completely escapes it. Okay. So reheating will clearly create a heat affected zone. And if you look at the crystallization content, it also varies with the power of laser that we use. Okay. So I'm considering 3 different powers. Okay, if I look at 200 watt, 250 watt, and 300 watt, you always see whatever power or speed combination you get, crystallization is unavoidable because you have reheating which occurs during the second scan you do or formation of the second layer over the bed. So we have to live with it. So the lesson is we cannot eliminate crystallization completely. It can be reduced with lower power, okay, but cannot be eliminated completely. Okay. And if you use lower power, the lower and lower power you will form lack of fusion. So another dilemma, crystallization porosity dilemma. Okay. So we are again back to dilemma which we talk about formation of metallic glass. Now the strategy to change this, and of course the problem with crystallization, as I already told you, material becomes brittle. So this material is extremely brittle. You make a metallic glass, you want a very nice mechanical properties, you 3D print it and immediately go out, it breaks like a biscuit. Okay, so that's not good. So what are we going to do? We are going to make BMG something that is still useful. Okay, and to do that, what we are going to do is we are going to mix niobium powder, age-old method of mixing niobium powder with your zirconium powder. And I'll tell you why we use niobium in a short while. And what we do is we are going to use 2 feeders, and then we are going to feed it through the nozzles of this. And as you can see, these zirconium 50 powder, zirconium 50 is the name of the metallic glass we are using, and niobium powder together in the laser beam is shining and you form a particular molten pool. Very, very similar to laser powder bed fusion. Only thing is you're depositing along with printing. Okay, you're depositing the powder as well as printing. Instead, where in powder bed, the powders have been laid down. Okay, so you again have a molten pool in both cases. And you can build very nice builds with this. Your niobium powder does not melt mostly, and it remains as a composite. So you'll have these inclusions that were there in the titanium part. Now these are going to be a amorphous crystalline composite. So it is zirconium niobium or zirconium metallic glass with crystalline niobium composite. And why niobium was chosen? A niobium undergoes plastic deformation via dislocations. And we have seen in literature that these kind of ductile particles, crystalline particles, they will trap shear bands because they are softer, and they will undergo plastic deformation resulting in strain hardening. So niobium is very nice for that. The other thing is niobium does not dissolve too much in glass. It has very limited solubility in the zirconium composition that we have used, which means that niobium cannot interfere with the glass composition. If it interferes, there is a possibility that it will form some intermetallic phases. If niobium forms some compound with zirconium, it's a bad thing. So since it has low solubility, niobium will always precipitate out even if it melts. So that was the idea of using niobium. And we are now going to look at the structures after printing. What we did was we did a monolithic BMP, which means zirconium 50 only we printed, 2 nozzles containing only zirconium 50. And we see, of course, this metallic glass matrix along with a crystalline band that is there. You can clearly see that, and the build direction as well as the longitudinal direction have been specified. Okay, and of course, this zone contains crystallites. We did the TEM analysis also, very small nanocrystallites of copper 10 zirconium 7 and I think copper 2 zirconium as well. Okay, and if you look at the composite now we did 2 powers. One we did a very low power, which is about I think 600 watts power we used. And at 600 watt power, what we saw was that you will have this niobium, okay, which is hello, somebody is there. Yeah, we have this niobium, and these niobium particles are irregular shape. If you remember, I had shown you that niobium particles have irregular shape, and these niobium particles are scattered all around it. In fact, even within the crystalline bands, you will have the niobium particles. Okay. Can you please switch off your microphone? I think, yeah, okay. So if you see these crystalline bands now have these niobium particles which are also embedded, and we saw that it's taking about 50% of the crystalline bands, and the shapes of the niobium is also retained. They're irregular shapes. Okay, and of course we have shown this insect to show that the niobium particles actually have a bimodal distribution of sizes. And if I go at higher powers, so this is called HNB-ZR50. So I am using a higher power of laser, it's 800 watts. I see that the niobium particles, the larger ones remain in the same size, but the smaller ones now have a very different shape. They are looking like a dendritic structure. They are not irregular. They have a dendritic structure, very regular dendritic structure. So some melting has taken place, but since niobium is insoluble in this metallic glass, it precipitates out as dendrite. That's what we were able to find out. So higher power leads to some melting of niobium, obviously, and that niobium gets rejected while cooling down. But interestingly, all this niobium is scattered throughout the matrix, but also within these crystalline bands, which means that the volume fraction of these nanocrystalline bands, right, which were forming due to reheating, is reducing. It reducing to 50%, reducing by 50%. Okay. And now what we saw, we wanted to look at the interface between niobium and metallic glass. On the left side, it is metallic glass because it's got a circular halo, which means there is no diffraction spot. On the right hand side, niobium crystal structure BCC, you can clearly see this spot pattern, this diffraction pattern, very clearly showing you this particular phase is a BCC phase. And you see that there are these crystalline, you can see these lines of rows of atoms essentially, or rather rows of these fringes, or rather, which shows that it's a crystalline material. And the interface is very sharp. So from glass to this crystalline, you can clearly show a line where this separates. Okay, so crystalline amorphous phase are highly separated. On the other hand, if you look at the high power case where we had used higher power, the glass and the niobium are now intimately mixed, and there is a graded interface. It's not a sharp interface anymore. The lines of this crystallization and the glass matrix have sort of interdiffused to a certain extent. Of course, solubility is not very high, but the interface is more graded in this case. Okay, and this has very good implications because what we now try to also look at is what happens to the structural state. Okay, we'll come to the implications in a short while, but structural state, we saw that the higher power case, of course, the structure relaxation is more, slightly more, and the lower power case, structure relaxation is slightly less. Okay, but when we did the uniaxial tension test, what we saw that they are all bad. Okay, the monolithic The metallic glass is bad as well as the composites are bad. But we thought we are only going to do compression, right? We are going to look at all these implants under compression or maybe let us say bending. So compression test is more important in this case. And what we see is very interesting. We see that the one which has made it higher power, and remember both of these contain 50-50, zirconium 50 and niobium 50. Zirconium 50 is the name of the alloy. Both are 50-50%. And you see that the one which has made it higher power exhibits great amount of strain to failure, right? About 4%, whereas the other two cases only 2%. And even the monolithic glass is terrible. I mean, it's not at all showing enough strain to failure. So this is, we have been able to make a very brittle material, a little plastic, by adding and making sure that it's melted a little bit. Okay. And to understand what this melting does and what this graded interface does, we looked at the deformation mechanisms after the sample failed. And you could clearly see that slip bands in the niobium, the case of the material which was made at lower power, which is 600 watt, we see that the slip bands don't transfer to the metallic glass that easy. Okay. So what really happens is there's a stress concentration that is created during loading because the load transfer is not smooth. There is a crack that. On the other hand, if you look at the one BMG composite with niobium, which was made at higher temperatures, the interface has become now graded. It has a gradient, and because of that, your slip bands can transfer slip to the metallic glass much more easily, and you can see more number of shear bands are formed. In fact, we looked at a zoom snapshot because several shear bands are formed because of effective slip transfer between the metallic glass and the dendrite or the niobium dendrites, and that actually delays the onset of crack, which means you'll have greater amount of strain to failure. So graded interface makes a lot of difference. And with that, we can show that even if you have crystallization in BMG, we can successfully make a composite. See, here in this case, we are stuck with crystallization. We have no other option but to wait for crystallization. But even in that case, we can make a composite that can still show good deformation characters. And that is the biggest thing in this in situ composite method, where we add niobium to make the material better, okay, without too much loss in the Young's model. So in summary, if you look at it, the innovation in terms of making these composite materials or making these in situ alloys, there is a lot of scope for it. A lot of research and additive manufacturing there, which is trying to make sure that we can do it cheaply. And cheaply, why? Because if you look at a master alloy of titanium niobium 45%, very difficult to make because you need to first alloy it, then you have to break it down to powders. Of course, the cost goes up. So rather having these niobium powders and titanium powders mixed in situ, making you essentially make a much cheaper alloy, right? Similarly, metallic glasses also, if you want to use a metallic glass implant, you can use niobium powder and you can create some kind of innovation to improve its mechanical properties. So we also saw several variations in process design. We generally assume that we look at a single bead test, but it's not necessary. We need to also look at how the entire build behaves and also how the melt pool dynamic changes when we use a different strategy or a different spot size or a different spot or you could say a spot type. Okay, it's either a Gaussian profile or a top hat profile. So these material challenges that are there in some cases can be synergistic or can be complementary when your 3D printing is concerned. So with that, I would like to thank you all. And we are at the cusp of this fourth industrial revolution, which is third industrial revolution, industry 3.0. And I hope that all of you enjoy and also leap into this additive manufacturing consortium. And with that, I thank you all for your patient listening. And I would be very happy to answer your questions. Thank you very much.
Yeah, thank you, Dr. Lakshmi Narayan, for a very insightful talk on processing of various material in additive manufacturing, especially what are the challenges are there related to that. You address very in depth. I hope participants also might have enjoyed your session. Okay, with this, I request participants to pose the questions. Maybe unmute yourself and ask the question directly, or otherwise you can write it in the chat box. I will take up your questions.
Dr. Subbu.
Yeah, please proceed.
Yeah. Thank you, sir. Good afternoon, Dr. Lakshmi, sir. Sir, it was a very nice talk. I just had a few doubts with regard to the initial presentation. Sir, you said that in general, like keyholing is a bad phenomenon in this case. But sir, but doesn't keyhole increase the laser absorption due to multiple reflections? And in that case, if you're able to control the porosity, wouldn't that be like a better option?
Yeah,
because we can get a deeper melt pool in this
you're
case.
right. You're right about energy absorption. That is absolutely correct. But problem is keyholing is always associated with porosity because you are going to move the laser. Wherever the laser movement is going to happen, you are going to suffer from porosity. And that is a bigger problem for structural lenses. But as you said, you can ensure homogeneous melting. But there are other ways also to do that. Of course, there are remelting strategies also that have come up. But that takes double time. But essentially, it depends on what you want. So if you're not using a structural material, then keyhole is not such a big deal. Keyhole porosity is not such a big deal. Okay. So from the structural integrity point of view, I look at keyhole as a problem, and it leads to greater porosity. See, the other way, if you look at the other melt pool shape that I showed, right? If you look at a wider melt pool, that also ensures homogeneous melting. So you can retain the energy in a wider melt pool, and the aspect ratio can be lower. So you can achieve both these things. Okay, of course, a little bit dimensional accuracy goes away with that. I agree, but you can achieve both these things. You can ensure no porosity as well as homogeneous melting with that strategy.
Yeah, sir. And sir, when you mentioned that your titanium alloy, you were using a top hat strategy.
Yeah.
But in that case, sir, if you are inputting too much energy, won't that increase the vaporization of titanium when you're trying to mix it with niobium? So how is that problem was there in your?
Somehow it did not happen. So what really happened is generally the thing is the heat distribution on the laser profile is actually great in the sense that of course you could always have a little bit of vaporization. I don't know how much of it did, but we found that the composition was very close to what we wanted. So some of these things are of course serendipitous. To achieve them all of a sudden, if you say, oh, let's go with it. But I can acknowledge that it is a possibility. That's why we can't go for two very high power. We stopped at 950. Higher we go, there are other problems.
Yeah. So, coming to this metallic glass, since you say that they are cooled at a very faster rate, so won't that induce some sort of thermal residual stress in the part? Yeah. So how did that affect the part properties?
That's a very good question actually, and I'm very glad you asked that. When we were printing these metallic glasses without niobium, we were having crack in the material. So adding niobium does another thing. It actually takes these stresses, because it doesn't melt. It can absorb these residual stresses very well. It can deform slightly and absorb these residual stresses. So cracking was prevented. So we were able to make crack-free build because of adding niobium. So that's the third reason we added. I didn't mention that, but fantastic that you mentioned.
Oh, yeah, thank you. And sir, you also mentioned that because of reheating, some crystal bands are forming in this bulk metallic glass. Sir, can electron beam powder bed fusion be used? Generally, we keep the base plate at a much higher temperature. So with that process, is it possible we can avoid this crystal band phenomenon?
Yeah, your knowledge is very good on this. This is a good question, but problem with metallic glass again. If you heat the bed, the relaxation starts, and we don't like relaxation at all.
Okay.
Yeah, glass is bad relaxation, and it's very sensitive to temperature. We want glass to be away from temperature. Unfortunately, in additive manufacturing, they have to raise it.
Yeah. Okay, so yeah, that was also. Thank you, sir, for such a nice talk.
Thank you for the great question.
Okay,
yeah, and I have a very quick question.
Yeah, please.
I just need to know the view of yours. Thinking about the thermal residual stress on the processed parts. How about going for a focused microwave beam instead of a laser in a additive manufacturing part? How is going to be a view on this?
Sorry, can you just come with the last part?
Instead of a laser beam, how about a microwave focused beam, microwave processing of the surface? Because we are going to deal with probably not more than 2.5 mm of thickness of layers. Best thing is going to be around like 30 microns. 50 microns. I think like instead of laser, how about your view on using a microwave focused beam for AMPRA?
Yeah, I think you are right. It can be used. It definitely is something which people are working on. Microwave technology right now for ceramics much more used because it sort of does some kind of sintering. Now sintering, there are some issues. If you don't completely melt it, of course, there's going to be issues. If you melt it, it's a different story. You have solidification things coming in. But sintering, if you're just going to sinter the material with some kind of energy input, then there are problems because sintering you can never eliminate pores. Your pores are you can never have full density. So that kind of a problem comes in. But if your microwave technology can be used to melt the material, sure, why not? I mean, only thing is your dimensional accuracy also needs to be, you need to properly focus that radiation so that you're able to maintain that particular shape that you want. So, but that's a nice point, and I think microwave technologies are coming up as far as I am aware.
Yeah, because like incorporating multiple technologies into a single process, what we are moving towards anyway.
Yes.
So I think true.
Actually, yes. In fact, I didn't talk about another field I work in, which is this WAM. It's called this wire arc curriculum. Very nice method, very cheap, and for the Indian context, definitely something which is very exciting because you don't, it's much cheaper and something which we also understand very well. It's like having a welding torch and attaching it to a robo, and that gives you some excellent microstructures and very nice properties.
Yeah, when we are even like working on some similar things now because the friction stir welding, we are incorporating microwave focused beams and vibration technology into weld repair issues of the fuel tanks. Yeah, we are even working.
Yeah, so that is what makes it exciting, right? So you use a power source and you attach it to a robo. So that just makes additive manufacturing exciting.
Exactly. Yeah,
that's very nice.
We get things sorted for multiple purpose, no? When you do one or two things,
and this technology is here to stay, right? I mean, because you can see the benefits, you can see how it has revolutionized the manufacturing sector itself. Different power sources come up every day. You talked about ultrasonic as well. So many things are there. They are using now spray coated additive manufacturing. That's also an excellent field. So
previously they used to have a flame torch for localized heating, but there are like various options now to go with laser or microwave, whatever it is. Yeah.
Right. So my whole point is, see, if you look at it, I am more excited about the point that manufacturing is now coming very intimately close to metallurgy. In the sense, because I am a metallurgist and I really feel that the type of microstructures and the type of engineering that comes in, kind of mesostructures that are produced, it's phenomenal. In fact, I didn't show some of the results we had for fatigue and fracture, but it outperforms even conventionally manufactured steel by a huge margin, twice or thrice. So it is fantastic, and it's very exciting for me.
Yeah, we have we can play with microstructure and we play with eventually the properties. Yeah, that's the basic of metallurgy,
Absolutely, absolutely.
Yeah, and that was a good presentation. Yeah, I liked it. Yeah, thank you.
Thank you.
Yeah, thank you. There are a few questions in the chat box.
Okay.
This is from Dr. I will. This is from Dr. N. Jayan. So what he has, do we have any facility for bioprinting in India?
Bioprinting, I think, unfortunately, I'm not very aware of the Indian scenario because since I came, COVID started.
Okay.
So
you are also belongs to COVID batch then.
Yeah, you could say that.
Okay.
But fortunately, my research didn't get affected. But bioprinting,
that is great.
Very few people, tissue printing is sort of something which I heard in MR 2018. I don't know how well India has adapted to it. But I have heard some of the research groups trying to work on it. I have heard of some faculty in Delhi trying to do it. But unfortunately, I'm sorry, I can't help you in that. I don't know any bioprinting. Sorry for that.
Okay, thank you. Yeah, so other question from Abhishek Divedi. He asked about, he wants to know some topics of research under Industry 4.0 for production and industrial engineers where we can pursue our research work.
Oh, I mean, you guys are the best time if you are a process engineer. There is no better time to be on earth than right now because look at the avenues of printing, look at the avenues of manufacturing. It's just mind blowing. And India, even if it adopts, say 20% of that, the number of jobs that are going to be produced, the number of research avenues that are going to be produced are phenomenal. I just now had a chat with Dr. Ashwath. I think he just mentioned the kind of avenues that are there. Each energy source that you can think of, you attach a robo with it and you can do wonders. So you look at every component. You look at power source, there is some something to do. You look at the material production, there is something to do. You look at material flow, there is something to do. Material mixing, there is something to do. And the choice of material you have. So every engineer who is now in the manufacturing sector has a new ray of hope. So definitely this is why it's a revolution, because there is not a single method. There are about 10 to 15 methods that can be used in different ways, and you can make phenomenal compounds. And I'm not telling that they are inferior to them. They are superior to these conventional manufacturing compounds. That is what makes it exciting. So there's so many opportunities in each field I listed. See even the powder bed engineering. You can change the temperature of the bed. You can change the type of lasers that you're using. You can change the type of power sources that you're using. And some people have done very we tried also something very interesting in VAM. We deposited some inoculants while printing. Very interesting stuff. A lot of innovation is there even for small scale industry. So I believe that this is definitely, this field is where you should target all kinds of innovation. Of course, if you couple them with things like machine learning and other tools, AI tools, there is a whole other bunch of opportunities to be had, especially in interdisciplinary research and opening a company which does all that.
Yeah. Thank you. So this is a question from Ponnarasan. He asked about porosity is a major concern of cracks are occurred in conventional and AM pots. Porosity is majorly contribute to any shear or even fatigue pots, like that he asked the question.
Okay. So yeah, that's a good question. Generally, fatigue is a surface superficial phenomenon. Superficial as in it occurs in the surface. Okay, I shouldn't call it a superficial phenomenon. Or rather, you could say that superficial feature on the surfaces causes fatigue. Any sort of kink or any sort of defect on the surface causes fatigue. So that was initially the understanding. After additively manufactured components, even if you do a very nice surface polishing, they saw failures to occur, at least fatigue as well as for ductility purposes. These porosities were leading to these fatigue cracks, and it's very, very clear. How we saw is that after the part failed, we look at the fractured surface, we can see a very clear circular blob, okay, and that blob has essentially caused the fatigue crack. So this is how we feel the fatigue porosity is a bad thing for all of us. I hope I answered it.
Yes. Okay. I hope even Ponnarasan might have listened that one. Yeah. This is from Mohammed Rafiq. Okay. So what he has that does agglomeration of the particle occurring when mixing of materials like say hybrid material like niobium and the zirconium 50, whatever you talked about, or passing through a nozzle onto the bed? If it is happening, how it is managed?
So fortunately for LDED, agglomeration does not occur. It can happen in laser powder bed possible, because when you're doing the spreading, unless you have a control over the dynamics of fluid, this is where chemical engineers also come in. You need to understand the dynamics of particles in powder bed. This agglomeration can occur, and to prevent it, they make it as dry as possible. That's the best way. Or while mixing, also they try to inject a lot of steam so that the bed remains little fluffy. So it's just like how you puff in a lot of steam or a lot of air in some of these cereals that you have, so they become puffy. So they do that. They gas with a lot of inert gases. They pass through and they keep it de-agglomerated. Otherwise, it can definitely occur. All of these forces, attractive forces, they come in. A lot of fluid bed mechanics guys are involved in those processes. But more importantly, it can be avoided if you have very good mixer strategy. And a lot of researchers have, a lot of patents have also come up on mixing strategies. So to some extent, there is some success, and the best method is, of course, as I said, keeping things dry and adding a lot of these inert gases to sort of keep these particles separate and then ensuring good mixing. The second part of the question, if I want to say for LDED, this problem is not very severe because you have two separate beds. You have two separate containers, not beds, two separate containers through which the powder is pumped through. And the moment the powders come in contact with each other, you have a laser peak melt. So the problem of agglomeration is immediately sorted out. We make sure that, of course, niobium will segregate, and that could be a problem. But we maintain the flow to some extent so that it doesn't niobium does not pile at the bottom. So the flow has to be adjusted to such an extent that niobium and zirconium 50 are melting and fusing, or not melting, both are not melting. Zirconium 50 is melting and niobium gets embedded in a reasonably homogeneous fashion. Of course, full homogeneity is not ensurable because of the irregular shape of the niobium particles. But if we keep the volume low of the melting, we keep the melting volume low, we can ensure reasonable degree of homogeneity. So that is how we tackle it in LDE.
Okay, yeah, thank you. So no more questions from the participants in the chat box. So maybe participants, if you have any more questions, please unmute yourself and then pose a question to Dr. Lakshmi Narayan.
Yeah.
Hello.
Yeah. Hi.
Yeah, I think no more questions from the participants. So that is the case. Like, yeah, I would like to thank you, Lakshmi Narayan, again for it's a nice talk. Actually, even you have presented the paper which is going to accept in additive manufacturing journal. It's really nice. Thanks for sharing that knowledge also with us. Okay.
Yeah.
So, yeah, we will wait some other time. Yeah.
Yeah, Lakshmi, thank you. Sorry, I joined only late at the end of your talk, but it was nice listening to your talk at the end. So, yeah, thank you.
Thank you very much, Professor Keshavan. It's all because of you. Thank you.
Yeah, nice. Okay.
All right. Okay.
Yes. Bye.
Thank you.
Yeah, thank you.
Thank
you. Yep.
How do I stop sharing?
Maybe no, you have that option, correct? Stop sharing, or you like leave the meeting.
Okay, I leave the meeting.
Yeah, then it is easy. It will go. Yeah.
Leave. Okay, got it. Thank you.
No problem. Yeah, thank you. I also just pause the recording.